All right, my name is Zach Jackson, and today I'm going to be going over an application of the Frenet array frame. The goal of my project is to see how the Frenet array equations apply to real-world problems. To accomplish this, I will explain the steps needed to calculate the path of a rocket through the atmosphere. The idea for my project comes from a scene in a movie about Katherine Johnson's time at the Apollo space program. So here's the clip here.
Ruth, get me the. You think you can find me the Frenet frame for this data using the Graham-Schmidt?
Orthogonalization algorithm? Yes, sir. I prefer it over Euclidean coordinates.
All right. So before we go through and try to, do a real world example, we kind of have to know the relationship between the components of the Frenet array frame. And so what we're trying to do is get the relationship between the derivative of the normal vector with respect to the arc length, and how that equals the negative curvature times the tangent vector plus the torsion times the binormal vector. So to start off, we're just gonna replace the normal vector with the cross product of the binormal and tangent vectors, and then what we'll do is do the product rule for cross products. And so basically that says the derivative of the first cross the last plus the derivative of the last cross the first, and so we get this little equation right here. And then next we're going to go over to our key over here and start plugging in values. So we're going to replace the derivative of the binormal with the negative torsion times the normal, and the derivative of the tangent, we're going to replace that with the curvature times the normal. And so next what we'll do is the anti-commutative and the scalar property. Because this is a cross product of vectors, it matters what order they're in. So if we switch the order of these, then that will change the signs. And then because torsion and curvature are scalars, we can just bring those out of the parentheses and bring those out front. And so now what we'll do is we'll do another substitution. Because NB and T are all orthogonal to each other, we can know that the cross product of any two will give you whatever isn't there. So the cross product of T and N equals B, and the cross product of B and N is T. And so we see that here. And so now we pretty much have the same equation here, just flipped around. And so we just flip those around and have negative curvature times the tangent vector plus the torsion times the binormal vector. And so normally what we would do it as far as like math class is concerned is take a curve and calculate the frame from there, doing the whole processes and whatever we did in class. But in relation to the video, trying to emulate what Katherine Johnson had to do, what we are going to do is take a set of just random vectors. They're not even going to be orthogonal, and do what's called a Graham-Schmidt process to make them orthogonal. And then from there, we can get our Frenet frame. And so the vectors that we start off with can represent things like forces acting on a rocket during takeoff reentry, such as the thrust and the drag, which would both be the same vector. Just you would just get the difference between the two. Gravity and the centripetal force would be the other two, an example of other two vectors. And so this kind of is the process that we're going to take. So we're just going to start off with three random vectors going in random directions, and we're going to compartmentalize them into orthogonal vectors. So basically, what the Graham-Schmidt process is saying is we're going to take one vector and keep that. Just say this is like our thrust, which would be like our tangent vector right here. We're going to keep that one and use it as a reference point, and then project the other two onto it, and then subtract the projection from the random vector, and then from that we get an orthogonal one. So for example, for this one right here, we would project it onto the tangent vector and subtract this vector from subtract the projection from this vector, and we would get an orthogonal vector. And we would do the same thing with this one. The only difference being we would project it onto both the original vector and the new orthogonal vector of our second one. And so here's kind of like a little video that we can visualize this process happening. So this is the first vector right here, and this is our second vector. We're projecting it on to the first vector, and then we're going to subtract the projection from the actual vector and get our orthogonal one. And then we're going to do the same thing with the last vector, this time projecting it onto the first vector and the new orthogonal vector as well. So here's the first projection. We're going to subtract to make it orthogonal to that one. And then we need to project onto the second vector over here to make it orthogonal to this one as well. And now we have three orthogonal vectors that are all orthogonal to each other. And so here we can divide by their magnitudes and get unit vectors. And so now we have the three vectors we need to make a T and B frame. Like I said earlier, we can represent the first vector as our tangent and then assign the second and third vector to the normal and binormal vectors. And now that we have our T, N, and B, we can kind of use that to calculate the curve that the rocket takes through space. We can calculate the curvature and the torsion from here. And then here are my sources right here. Got it in the MLA format and everything. So there you go.